Recall that in the last lecture we saw the definition of a topology, which we denoted as tau on a set X, and we also saw the example of a topology which was just the collection of the empty set, and the set itself is a topology. We proved that this is a topology on X, and this topology has a name. It is called the indiscrete topology. So of course this means that any set has a topology, and this indiscrete topology is one of the possible topologies that a set can have. Now let us continue this discussion and talk about other examples of topologies. And so continuing with example, so this is the second example, and this is taking the collection tau to be the entire power set of X, and this is a topology on X, and this is called the discrete topology on X. So let's see why this entire power set is itself a topology, and this is very easy because, well, phi and X are subsets of X, so they belong to the power set. Secondly, any finite intersection of elements, finite intersection of subsets UI is also a subset of X, right? Because everything is taking place inside this set X. So if you take a finite intersection, then also it will be a subset of X. This means that the finite intersection of these UIs are of any subsets, okay? Because these UIs are any arbitrary subsets of X, and this means that the finite intersection is also in the power set. Similarly, if you take the arbitrary union U alpha over some index set J, this is also a subset of X, as we have seen, and this means that the arbitrary union of U alphas is in tau. So we see that this topology, the discrete topology, is also a topology on the set X. Now these first two examples, the one is the indiscrete topology and the discrete topology, are in some sense not very interesting because well, there are no interesting open sets. So what are the open sets for the indiscrete topology? The open sets are just the empty set and the set itself, and the open sets in the discrete topology is any subset of X. So any subset of X is an open set in this topology. So many times we want to restrict the what kinds of open sets we want, so that we can get interesting results. And the indiscrete and discrete topologies are perhaps not very interesting in most cases. So then let us see an example of a topology which is neither the discrete topology nor the indiscrete topology. And for this example, I will take X as the 2-point set A and B. Okay, so it's just a 2-point set, and we can define several topologies on this set X. So the first one is, of course, the discrete topology, tau discrete, which we have seen, and this is just the collection of all subsets of X. So this is the power set. So it has the empty set, the set itself, and there are other subsets such as A and B, and these are all of them, right? So this is the power set of X. So this is the discrete topology. On the other hand, you have the indiscrete topology, which is simply just the collection of phi and X. So we have seen that both these are topologies. Now we can define some other topologies as well. So this is the collection of phi, X and A. So we exclude the singleton set B, and one can check that this is also a topology on X. For example, if you want to take finite intersections, of course, if the open sets that you consider only phi and X, then of course the finite intersection will be either phi or X, as we have seen in the case of the indiscrete topology. So now if you have say n open sets ui, and at least one of them is A, and none of the other ones are empty, so ui's equals either A or X. Okay, so then the intersection is going to be just A. So as you can check, then the intersection is simply A, because A is a subset of X, and when you take the intersection you get back the set A. So this is just one example, and there are other cases that you can consider, and the finite intersection property for the topology can be checked for this tau 3, which is then a topology. Similarly, the arbitrary unions can also be checked. So I leave this as an exercise to show that this is a topology on X. Now notice that this set A can also be replaced by the other point, which is B. So that's yet another topology, so which I call tau 4, which is phi, X and the singleton set B. This is also a topology on X. So we see that there are other possibilities of topologies given a set. We can try and form other topologies on that set, and some of them will be more interesting than the others. Now yet another topology. So this is another example of a topology on an arbitrary set. So let X be an arbitrary set, say non-empty, because that will be our main interesting example where the set itself is non-empty. Okay, so any arbitrary non-empty set. Then define tau to be the collection of subsets U of X such that the set difference X minus U is either all of X. Okay, so the set difference X minus U is equal to X, or it is a finite set. So this set difference X minus U is usually denoted as UC, and UC stands for U complement. Okay, so or the complement of U. And so this is by definition this set difference X minus U, and because of this topology tau is called the finite complement topology, or also sometimes cofinite topology. So we have to show that this tau is a topology. Okay, so to show that tau is a topology on X. So let's see a proof of this fact. So the first property that we want to show is that both the empty set and the set itself are in this collection. So of course X is in tau since the complement is empty because it is X minus X. So you're taking all this all the elements and removing from are removed from X. So because X complement is the empty set, which is a finite set. Remember that empty set was a finite set by definition. And also the empty set belongs to tau since the complement of the empty set is now the entire set X. Okay, so X minus the empty set is the entire set X. And now this is also so this is now an allowed element of our collection because we took the complement was either X or it is a finite set. Okay, so there are two different ways to have this complement in our topology. So for X we saw that the complement is a finite set, which is the empty set, and for the empty set we see that the complement is the entire set. And so this is also so the empty set also belongs to tau. Now let us check for finite unions. So for let u1, u2, un be elements in this collection tau, which means that for each one either the complement is all of X or the complement is a finite set. And now we have to show that the intersection of ui's I equal to 1 to n is in tau, which means that, which is the same as saying that either X minus, so let me write it as complement, ui I equal to 1 to n, entire thing complemented, which is just the set X minus this set, this intersection is either is X or a finite set. Okay, so so we have two cases here. So if the intersection ui I equal to 1 to n is empty, then the complement ui complement is X minus the empty set, which is X. Okay, so in this case we have that this is in tau. All right, this was the first criteria for a set to be in tau, which is that the complement is the entire set X. On the other hand, if the intersection I equal to 1 to n is not the empty set, then what happens? So then I claim that the complement is a finite set. Why is this? So let's see. So if you take the set difference of this X with this intersection, then this is equal to the union I equal to 1 to n X minus ui, which is the same as saying that this is the union of ui complement. This is a set theoretic rule known as De Morgan's law or the Morgan's rule, which allows you to write the intersection, the complement of the intersection, as the union of the complements. Okay, so complement of intersections equals union of complements. So I leave it as an exercise to check, check that this is valid, okay, for finite intersections. It is also valid for arbitrary intersections as well, as you can check. So we only need it for finite intersections, and we have this property that the complement of the intersection is the union of these complements. Now because ui is in tau, okay, for all I in 1, 2 up to n, this means that a ui complement is either x or the empty set, or a finite set, sorry, or a finite set. So what happens in the case that when all of them are in X, or if at least one of the UI complement is X? So let me write this down. If at least one of the UI complement is equal to X, then this finite union of UI complement is going to be X. On the other hand, if at least one of them is equal to X has been taken care of, so if all the UI complement are finite sets, then this union I equal to 1 to n UI complement is a finite union of finite sets. Which means that this is a finite set. As we have seen, this was one of the important properties for finite sets, that finite unions of finite sets is a finite set. So this means that this finite intersection is an element of our collection tau, right? Because this is simply the complement of this finite intersection. Alright, so similarly we can handle the arbitrary union. So we have seen this is for the second one, this was for the finite intersections. And the last one will be for arbitrary unions. Arbitrary unions. And so for this, let U alpha be an indexed family of sets in tau, and we have to show that the arbitrary union of these U alphas is in tau, which is the same as saying that the complement of this is either all of X or a finite set. Okay, so let's see why this is true. So if all the U alphas are empty sets for all alpha in J, then the complement of the union. So this is the union is then just the empty set, as we have seen, because it is the union of empty sets. And this is the complement is just the complement of the empty set, which is X. So then this is in tau. On the other hand, if all are non-empty, if all U alphas are non-empty, then the complement U of this union is actually again by De Morgan's law. So the first one was that complement of finite intersections is union of complements, and this is the other one which says that complement of union is the intersection of complements. Okay, so this is actually the intersection of U alpha complement. So this is again by De Morgan's law. De Morgan's law, which says that complement of unions is the intersection of complements. So now, since all of them are non-empty, this implies that U alpha complement is a finite set for each alpha, and this implies that the intersection of these U alpha complements, this is a subset of U alpha complement for each alpha in J, and because a subset of a finite set is always finite, this implies that intersection so I can go directly. So this is not an implication, this is just since the intersection of the complements is a subset of U alpha complement for each alpha, so then the complement is the intersection of the complements is a finite set, because subsets of finite sets are finite. So we see that the intersection U alpha complement is in tau, and this is exactly what we wanted to show, that the complement of the union, what I mean here is not the intersection but the union of the U alphas belongs to tau, because its complement is a finite set. So this ends our proof of the fact that the finite complement topology satisfies all the properties of a topology.